Chapter 9 looks at something called hybridization. This is kind of wild, so be patient. It's going to make sense. But sometimes this is a topic that, we'll come back at the end of the year and we start reviewing topics for the AP test, and people will say, what the heck was a hybrid orbital? So do be patient with it. It makes perfect sense. Here's the issue. Let's say we're looking at the bonding in methane, CH4. And a Lewis structure would be real simple. I'd have carbon with these 4 valence electrons, and then I'd hook on the hydrogens, 1 and 2 and 3 and 4. Piece of cake, right? Now think about what's really happening when we share these electrons. If I think about the valence electrons in carbon, let's sketch an orbital diagram. So we would have something that looks kind of like this. And I'm only going to look at the valence electrons. I don't care about the core electrons. They're not involved in bonding. So for carbon, the valence electrons will be in the second energy level. So we'll make this the 2s, and these will be the 2p orbitals. Carbon has 4 valence electrons, right? So we normally sketch them as 1, 2, 3, 4. Okay, so here's my 4 valence electrons. In my Lewis structure, it looks like we're going to share those valence electrons with the electrons of hydrogen, and everybody's all happy. But now look at where those 4 valence electrons on carbon are coming from. If I think about a carbon atom, I've got some valence electrons in an s orbital and some valence electrons in a p orbital. And if I think back to early atomic structure, p orbitals are supposed to be a little higher energy, right? So now, would you expect maybe that there would be a difference in the bonds? Those carbon-hydrogen bonds, would they be a little different if the carbon electron was coming from an s orbital versus a p orbital? Like the p electrons might be a little higher energy. So would that change the carbon-hydrogen bond if it was overlapping a p valence electron in carbon versus an s valence electron from carbon? Would some bonds be a little stronger, some bonds be a little weaker? And that's not the case whatsoever. All 4 of those carbon-hydrogen bonds in methane are exactly the same. They have the same bond length. They have the same bond energy, meaning it would require the same amount of energy to break all 4 bonds. But that doesn't really make sense if I think about a carbon atom. So here might be like the atomic orbitals of carbon. And I just kind of sketched them as an orbital diagram. These are my atomic orbitals. Do you see where I'm getting at here? If p electrons are higher energy orbitals, would that be like a higher energy bond? Like the 2 carbon-hydrogen bonds that involve the p electrons, would those be like higher energy bonds or something different than the 2 carbon-hydrogen bonds that involve the s electrons? And like I said before, it's totally not the case. For purposes of bonding, we need another model. This atomic orbital model, this doesn't give me a true picture of the bonding that occurs when carbon and hydrogen bond in a molecule such as methane, CH4. We need some kind of special bonding orbitals to explain the fact that all 4 of those bonds are exactly the same. That's where hybrid orbitals come into play. This is wild. It's great. You're going to love it. Okay, so we just said that these guys over here, these are atomic orbitals. Atomic orbitals. Cute, right? We got the S and we got the P's. The S is low energy. The P's are higher energy orbitals. for purposes of bonding, carbon makes these hybrid orbitals. And if you think about the word hybrid, it means, like a joining or a combination. And that's exactly what occurs. These special orbitals are for bonding. Carbon makes what we call Sp3 hybridized orbitals. It means just that. We're going to take the 1s orbital and the 3p orbitals from that atomic structure, and we're going to morph them together into 4 equal energy identical bonding orbitals, and we call them Sp3 hybrid orbitals. So right here I'm going to call these Sp3 hybrid bonding orbitals. And like it mentions up here, these are all equal energy. That's super important. That's why all 4 carbon-hydrogen bonds are exactly the same. We're not really dealing with different kinds of orbitals when we bond with carbon. Now, it's not to say that that first picture, that's not incorrect. In a carbon atom, yes, we would have the 1 spherical s orbital and the 3 kind of dumbbell-shaped p orbitals. And yes, they are different energies. But for purposes of bonding, carbon will hybridize or mix together all 4 of those atomic orbitals to make 4 equal energy bonding orbitals. And again, these are only for purposes of bonding. And now, can you see why it's called an Sp3 hybrid orbital? We take the 1s and the 3 p's. We mix them together and we get these equal energy bonding orbitals, 4 of them. Okay, so here again, here's kind of what we're doing. In the carbon atom, the free carbon atom, we would have had electrons distributed kind of like this. 1, 2, 3, 4. But when we're ready to bond, carbon will hybridize those orbitals into 4 equal energy Sp3 hybrid orbitals. And we're going to put one of those valence electrons in each of these 4 hybrid orbitals. Oh, and again, sometimes people will kind of question that atomic structure, and they'll say too, well, it really only looks like there's 2 places to bond because those 2 s electrons are paired. Isn't that supposed to be real stable? Maybe it only looks like we would bond those 2 p electrons. And we know that's not the case. We know that carbon wants to bond 4 times to get a full outer shell of 8 valence electrons. This new hybrid model, again, kind of gives us a better picture of how we're going to bond those 4 valence electrons. For bonding purposes, we kind of morph those atomic orbitals into 4 equal energy bonding orbitals called Sp3 hybrids. Now it tells me here, any molecules with shapes based on a tetrahedral structure will adopt these Sp3 hybrid orbitals. These orbitals are for shapes based on the tetrahedron. So obviously the tetrahedral, I'll write that down. So if we have a tetrahedron like the true carbon CH4 or something like that, if I have a tetrahedron as my Vesper geometry, that's going to give me these Sp3 hybrid orbitals, or any shapes based on a tetrahedron. So that would include trigonal pyramid. Remember the trigonal pyramid? Where I have 3 bonding regions and a lone pair. So if I kind of sketch these guys, here's my true tetrahedron with 109.5 degree bond angles. Here's my trigonal pyramid And then up on the top, we have a lone pair. So there's still 4 regions of negative electrons. It's just that one of those regions is a lone pair instead of a bonding pair. The other option would be the bent with 2 lone pairs. So kind of like water, where you might have 1, 2, and then I'd have 2 lone pairs. Or again, it's still 4 regions of electrons around the center, but only 2 bonding regions, and then the other 2 are lone pairs. All 3 of these shapes have 4 regions of electrons around the center atom. We're going to need these Sp3 hybrid orbitals. Okay, now a couple other things that are kind of interesting. I like this picture down at the bottom because it kind of shows what happens in covalent bonding. In covalent bonding, we're going to just overlap the bonding orbitals. And that's how we share the electrons. So can you kind of see in the center, I mean, on your study guide, it's going to be a little tricky because it's not in color. These are in your textbook if you want to see them in color again. You've got carbon. Around carbon, it'll show his 4 Sp3, 2, 3, 4. I mean, it's kind of in 3D, so it's hard to see a little bit. But around carbon, you've got those 4 hybrid orbitals, Sp3 bonding orbitals, and then they're just going to overlap with the 1s orbital of hydrogen. And then can you kind of see what they're showing in here? So here's the 1s orbital of hydrogen. Here's a 1s orbital, 1s, 1s. So can you kind of tell that they're showing 2 electrons? Whoopsie, spinning opposite. Hello. Get out of there. Spinning opposite. In a second. There we go. I'll try to make them a little bigger so you can see that. Down, up. That's what happens when we bond. Covalently bond. We just overlap those bonding orbitals, and then we share the electrons. Oh, now we don't have to hybridize any orbitals on hydrogen, because hydrogen only has 1 valence electron, and it's only involving 1 orbital, just the 1s orbital. So we'll overlap the 1s orbitals from hydrogen with those special Sp3 bonding orbitals of carbon. That's how we get these angles. We get these 109.5 degree bond angles because that's the angle of the hybrid orbitals. These hybrid orbitals, these Sp3 orbitals, are created at that 109.5 degree angle. They're all equal energy bonds, equal bond length, equal bond energy. So it's just a little different way of looking at this concept of covalent bonding, involving these special hybrid orbitals.